Right. So yesterday we were talking about this system that ud plus c of u here t greater than 0 and x is in R, and at t equal to 0, this is u naught x. This is a C1 function, let me say, and this is also C1 function with C dash u greater than 0. So yesterday we noticed, are you able to hear me?
Yes, sir.
All right. So yesterday we noticed that this initial value problem, which is quasi-linear, in fact, after a finite time, you see the initial profile is smooth, but after a finite time, the solution breaks down, right? The continuity of the solution breaks down. So the problem is how to extend the validity of this solution beyond this breaking time. So for that, what we do, we need to, so it's very clear, you see, that, I mean, that assumption which we used in the beginning, that the derivatives, they are of class C1 is no longer valid, So this ceases to be a valid description of the physical process, and we have to go back to the physics of the problem, that what went wrong in this formulation. We have to modify the model and proceed further. So what is the modification in the model? We have to replace, in order to extend the validity, because a discontinuity appears, right? When once a discontinuity appears in the flow, we have to, we cannot remove this discontinuity, but we have to extend the notion of solution, which includes discontinuities as well. So we are going to extend the notion of solution here, up to here for t less than tb, it was a smooth solution, right? But now we will talk about the weak solution. So in order to extend the validity of the solution, what we do first, we write this equation in the conservation form. We need to write this differential equation, let me call it 1, write 1 in a conservation form. What is a conservation form? Conservation form means we have to write this in the form derivative t of say u. U is a function of x and t plus derivative x of f of u. This is equal to 0. This is your density function. U is the density function, and this is your flux function. So you see, it's a very, the general form of a conservation law, this is the conservation of mass. If U is the mass density, and this is the mass flux, then it is this equation represents the conservation of mass in one dimension. If U is the momentum density, and this is the momentum flux, then it represents the conservation of momentum. If U is the energy density, and this is the energy flux, so is that right? It's a very general form of the conservation law. Look here, what does it mean? Here, f is a function of U, and in turn, U is a function of x and t. So this is the meaning that I can write this as f dash u, right, into ux. Am I right? Hello?
Yes, sir.
And this f dash u is nothing but c of u. C of u. So this is the same equation. Is that right? Same equation. It is written in this differential form where c is nothing but f dash u. Here c dash is taken to be positive. So here this c of u, this is nothing but your f dash. F dash u is c of u, and c dash is taken to be positive. So c dash means f double dash u is equal to c dash u is greater than 0. That is, the flux function is convex. Right? This is the density flux. This is, right, density function, and this is the flux function. So this is the conservation law corresponding to this equation. This equation has to be written in a conservation form. This is the first step in order to extend the validity of the solution beyond this breaking time. So here you can see that here the convex function, right? The flux function is convex. F is the flux function and it satisfies this condition, means it's a convex function. So there are large number of physical problems in which the flux function is convex. For example, the Euler's equations, which are derived from Navier-Stokes equations, as a particular case when there is no viscosity or thermal conduction. We have a convex flux function. But of course, there are physical examples where the flux function is non-convex. For example, oil reservoir simulation. Here, the conservation, this flux function is non-convex. Similarly, there are examples in plasma, MHD, and real gas flows, where the flux function is convex, so the situation non-convex, and when the flux function is non-convex, the situation is highly complicated. In fact, even in one dimension, there are open problems in the literature. The reason is this, that we do not know the stability criterion, that what should be the stability criterion that ensures uniqueness of the solution. This is the problem. So anyway, here we shall confine ourselves to the convex flux function. All right, so this is the differential form. Look here, I will call this as equation number 2. Differential form of the conservation law. This is the differential form of the conservation law. But perhaps you might have seen, because at your undergraduate level, when these conservation laws are written, right, you pick up any book on physics and you will find that when we derive a conservation, when we see a conservation law, it is always derived in integral form. In integral form. Integral form means the conservation law in the integral form is this, the derivative of u of xt dx from, say, x1 to x2. What it says, if u is the density per unit length, okay, say x1 to x2, if u is the density per unit length, then this integral from x1 to x2, this is the total mass contained in this interval. Is that right? This says that the rate of change of total mass is balanced by the net flux.
Daily on the no detail laptop.
Hello? Hello, Lakshmi.
Okay, sir. Nothing to worry.
What is the problem?
Some participant has just unmuted himself. That's.
Okay, all right.
You can continue, sir.
So this says that, so what I say that this is the conservation law in the differential form, but generally the conservation laws are written first in integral form. So this is the integral form of the conservation law. Integral form of the conservation law. Right? That is, rate of change of total mass is balanced by the net flux. So what is the flux at this point? That is amount the definition of flux, you may recall that amount of something coming out through unit area in unit time. Is that right? Along the normal. Along the normal. For example, in Maxwell's equations of mathematical physics, we say that divergence H is equal to 0. Means magnetic flux across a closed surface is 0. What is that? The number of magnetic lines coming out through unit area, unit time along the normal to the surface. So this is rate of change of this is balanced by the net flux. Net flux means amount entering into this. And flux across this means amount leaving this station. So here x1, this station is x1, this station is x2. So the amount of fluid entering into it, I will write f of u, is that right? F of u at x1, am I right? x1t, this is the flux entering this station from left to right, and minus, so it is the net flux, f of u x2t, yes. This says that rate of change, the rate of change of mass contained in this interval is balanced by the net flux across the boundary of this interval. So in a one-dimensional situation, this is the conservation law. Now you can see that if u is a function which is of class C1, both are equivalent. If u is a function which is of class C1, both 2 and 3 are equivalent. If u is of class C1, then both 1 and 2 are equivalent. Is that right? Because I can replace this x2 by x, right? This x2 by general x, and I differentiate with respect to x. So I get dy by 2 u is equal to dy f dy x, because this is something which is constant with respect, this is variables. So minus dy by f, and this transposing this term to the left, I get this result. So if u is of class C1, this is derived from here. But let me tell you that, but you see, this is more general as compared to this, in the sense that this form, the differential form of the conservation law, I mean, it is quite meaningful as long as u is of class C1, but it is meaningless for functions which are not differentiable. Is that right? Hello?
Yes, sir.
And much less, there is no meaning attached to it if you are discontinuous. If these functions are discontinuous, it is meaningless. But this form makes sense even for discontinuous functions. Is that right? We know that even if u and its derivatives are discontinuous, they have a finite jump discontinuity, then this integral exists. Is that right?
Yes, sir.
So that's why, as I said in the beginning, here this breaks down after a finite time. This differential form, I mean, this breaks down, solution breaks down after a finite time. In order to extend the validity of the solution beyond this breaking time, we consider the conservation law, the conservation form of this equation, the conservation form in differential form, and this is the corresponding integral representation. So our model would be now modified. This is our modified model. Same thing, the integral, I mean, integral written in integral form, conservation law written in integral form. Is it all right? Hello?
Yes, sir. It is.
And the reason is very clear, because after a finite time, the solution admits a discontinuity. The solution
Integral is valid, that's why it is fine.
and therefore, yeah, right. And therefore, we need the integral representation rather than, so the definition of weak solution. The weak solution, now we say that a solution of one, which is of class, this is x1, this is x2, and this is the discontinuity, because we know that this develops a discontinuity after a finite time, right? This admits, whether we write in this form or we write in this differential form, it admits a discontinuity after a finite time. Let us call this as x as a function of t. Okay, this is your x1, this is your x2. So in this region, in this equation is valid in this region, that is your ut plus f of x, this is equal to 0, this differential form, it is valid in this region. But definitely, I mean, it's not, it doesn't make any sense. This form doesn't make any sense on this. So we have to see that introducing this form, okay, integral representation of this conservation law, what does it enforce? What does it enforce? That we have to see. Is it all right? Hello?
Yes, sir. It is fine till now.
Oh, fine. So this left-hand side we can write. This is your derivative t. Now, if you look here, this integral is from x1 to x2, but a discontinuity appears in this region somewhere. It is not an arbitrary discontinuity that we have to find out that what is this discontinuity in fact. I mean, what this law says. According to this law, it should be x1 to x of t, right? We move from here to here, x1 to x of t, and this is your u of xt dx. Is that right? Plus I can write from xt to, yes, x2. Is that right? At this point, this function suffers a jump discontinuity. U and its derivatives, they suffer jump discontinuity at x. So naturally, I have to say, what is this? I mean, I would say that limit of u as x approaches x of t from left. Is that right? I'm moving from x1 to x2 in this direction. So as it approaches this, right, x is x minus u of xt. Is that right? So this is your, I will call it ul. That is the limiting value of u as the discontinuity is approached from left. Is it all right? Hello?
Yes, sir.
Yes, sir.
And similarly, I say that yes, from x2, from here to here, they're just on the right, because I do not know that behavior at this point. I do not know. But just on the right, it means u of xt as x approaches x plus. This is your ur. I mean, the value as we approach from right at this point, just at the right, it is ur. That is when the discontinuity is approached from left or from right, the values we denote by ul and ur. Is it all right? Hello?
Okay, sir. It is fine.
Yeah. So I will write u of xt dx. This is your left hand side. This is your left hand side, and the right hand side is f of, yes, it is same, f of u x1t minus f of u of x2t. All right, I will call it right hand side every time because I did not write it. I have to deal with left hand side. Let us see what do we get. So using Leibniz rule, what do we get from here? Leibniz rule, the first term we are going to get deva u deva t. Is that right? From x1 to x of t. Dx, this is the first term, plus this function evaluated at the upper limit. So in fact, what is this? It is nothing but u at what? xt on the left. Am I right? Hello? As
Yes, that value is.
xt from, yeah, right. So this is nothing but your ul. I will write this as ul.
You have to just use the Leibniz rule only.
Leibniz, right, correct. So, but here it is a constant, so here this vanishes, right? Into this is, we get dx dt. Am I right? Hello? Dx dt.
T. Yes, dx over dt. Yeah.
This evaluated at the upper limit multiplied by its derivative. And similarly here, but since it is constant, that term doesn't appear. Similarly here, when we make use of this, what do we get? This is xt to x2. And this is your, again, deva u, deva t, dx, right? This is the first term. Now, vanishes at the upper limit because this x2 is fixed. Minus this, so minus You evaluated at the, am I right? Hello? You evaluated at what? X plus. Is that okay? Into dx dt is equal to right hand side. Is it all right? Hello?
Yes, sir. It is correct right now.
Very good. So now yes. So what do we get? Look here, from x1 to x. This is the reason. In this reason, on the left of this discontinuity, this result holds. Is that right? Ut plus f of x is equal to 0. So I will replace this x1 to x of t. I will replace it by minus f of u, right? Its derivative using this result. Is that right? Hello? Is it all right? Hello?
Yes, sir.
Okay. And now you can see here, let's combine these two terms, this and the fourth on the left, that is u, this is your ul, this
Yes,
is
that is the left-hand side value.
so ul minus ur dx dt. Is that right? This is a
Yes, sir.
smooth function,
Yes, sir.
okay? This is a smooth function, across which the flow this field variable undergoes discontinuities. Is that right? So ul minus ur ddt of xt plus what remains? Again, it in this x2 to x. Again, in this reason, I can replace this dy u dy dy minus dy f dy x. Right, this is your right hand side. Is it all right? Hello? Is it okay? Hello?
Yes, sir.
Yes, sir.
Now making use of fundamental theorem of calculus, this x derivative, so this is nothing but its value evaluated at the upper limit. Am I right? Its value evaluated at the upper limit, that is u evaluated at x minus, am I right? X approaches x from left. Is that okay? Hello?
Yes, sir. It is correct.
So the value of this evaluated at the upper limit minus its value, so it becomes plus at the lower limit. That is f of u at x1t. Is that all right? Hello? Its value, fundamental theorem of calculus. Its value evaluated at the upper minus its value evaluated at the lower. Plus, I will call this as jump in u as a matter of fact. What is ul and ur? Ul is just at the rear. This is just at the rear. Ul here, and these are the contiguous points. Ul and ur. It is jump in u across this line of discontinuity. So I will denote this. These two square brackets enclosing this entity means its value on the left minus its value on the right. It's a matter of notation only. Is that right? Hello? Is it clear? Hello?
Yes, sir.
All right. So this is dx dt. And again, the same thing. I can make use of the fundamental theorem of calculus, and from here what you get? Minus f of, at the upper limit, right? Minus f of u of x to t. Is that right? Minus at this, so it becomes plus the next term, that is f of u of xt on the right, and this is just evaluated on the right of the discontinuity. These are left and right, these are the contiguous points on the discontinuity. Is that right? Hello? So this is equal to your right hand side. Now let us recall what is the right hand side. Right hand side was this expression.
F of u of xt minus.
Yeah, this is the one. This is the
Yes,
one. So f of u of x1t minus f of u of x2t. So look here, this term cancels with this on the left, this term cancels with this on the left, am I right? So what remains? And this is nothing but f of ul, am I right? Hello? I will say that it is the flux function on the left. Is that right? Hello?
Yes, sir.
So this is the jump in f, I would say. That this is on the right, f, the value evaluated on the right. So evaluate, this is on the left and this is on the right. So I will write this minus jump in f. Is it all right? Hello?
Yes, sir.
Yes, yes,
The
sir.
notation is ul minus ur. So f of l, it is on the left. Minus, so minus f plus u dx dt. This is equal to 0. Or we get this result, that jump in u, right? What is this? This is nothing but slope of the discontinuity, dx dt, right? It's the slope of the discontinuity, and in fact, this is your speed with which the discontinuity propagates, and this is your right f. Or since this is different from 0 because it undergoes a discontinuity, means ul is not equal to ur, so I can divide it. That is dx t. This is your jump in f divided by jump in u. This is called Hugoniot jump condition. Euler jump condition. So you see what a fantastic result. That is, if any discontinuity appears, so it is because of, instead of taking this as the conservation law, I have taken the integral form of the conservation law because it is more general. It admits discontinuities as well. And introducing this conservation law, it introduces this constraint as a matter of fact, that this condition has to be satisfied, right? If something is discontinuous from left to right, this must be satisfied across a discontinuity. Is it all right? So if there is a reason of discontinuity, right? If there is a reason in which a discontinuity appears on the left, your model is valid. On the right, your model is valid. But on the discontinuity, the model itself, yes, it shows, it exhibits that this condition must be satisfied. Is it all right? This is ensured by the conservation law. All right. So now so here you say, we will say U as a weak solution. U as a weak solution of this conservation law. U is a weak solution of this conservation law if U satisfies this Rankine-Hugoniot jump condition across the discontinuity which appears after a finite running length or finite time. We have seen that no matter how smooth is the initial discontinuity, initial data, a discontinuity appears in the flow. A discontinuity appears in the flow across which U is discontinuous. So this modified, conservation, this form, it suggests that across that the discontinuity, must satisfy this relation. U is discontinuous, F is discontinuous, they must satisfy this relation. That is, the velocity is nothing but the ratio of these two. This is your jump in flux, this is jump in density. So jump in flux, jump in density, or you see its reciprocal is nothing but the slope. Is that right? Dx dt is the velocity, but its reciprocal is the slope of this curve in the xt plane. All right, so let's take an example. Now, all right, so we have extended the notion of a weak solution, of a classical solution. We have extended the notion of a classical solution so that it includes discontinuities as well. But you will see that in this process, we have lost uniqueness of the solution on two counts. The first is, look here, non-uniqueness of the conservation law. And secondly is non-uniqueness of the solution of the solution. Because we'll see that non-uniqueness of the weak solution, I would say, non-uniqueness of the weak solution. So this is the problem at this point of time, that what do we mean by non-uniqueness of the conservation law? I have taken, for example, if I take ut plus uux equal to 0, right? One conservation law for this, I can say that u t derivative plus u square upon 2x derivative, this is equal to 0. This is one conservation law. Is that right? Hello?
Okay, sir.
I mean, this is your density function, this is your flux function, right?
Yeah.
It is in the conservation law, but I can have infinite number of conservation laws from here. If I multiply it by u, so you will see that u square upon 2 its t derivative.
Yeah. I mean, there exist many scalar field functions which can be.
Exactly. Is that right?
Yes, sir.
And not only that, I get a sequence of such functions, un upon 2. I keep on multiplying by u, and you differentiate because it is u du dy u dy t. It is u squared, isn't it? Dy u dy x. U gets cancelled, and we get this form. Is that right? Hello?
Yes, sir. Yes, sir.
So the thing. I'm sorry. N divided by t. And here you get un plus 1 divided by n plus 1x. So you see, from a given conservation law, I get a sequence of infinite conservation laws. And we will see that the solution of this weak solution of this conservation law is different from the weak solution of this conservation law. And therefore, I mean, all these conservation laws, they have been derived from the same equation, but a weak solution of this is different from a weak solution of this. That is, they are not equivalent with respect to the weak solution. Is it all right? This, we'll see it. How does it work? All right. So let's take one example. That is, this is the one. This is the example. All right. I take this as so these are the conservation laws. All right. Let us take this conservation law and say that what is the solution? Some initial condition is needed. I take this initial condition to be say. I take this to be on the left, say 0, when x is less than 0, and I take this as 1 when x is greater than 0. Is it all right? A problem of this kind is called, do you know what is this initial value problem? This is called Riemann problem. Riemann problem. This initial value problem is referred to as Riemann problem. Riemann problem, that is, there is a discontinuity in the region which separates two constant states. On the left, there is a constant state. So what is this solution? If you look in the ux plane, this is your ux plane. On the left, when x is less than 0, here the solution is u is equal to 0. On the right, u is equal to 1. So this initial, I mean, this is the initial condition which separates two constant states by a single discontinuity. Is that right? Such an initial value problem is referred to as Riemann's problem. Okay? So you know what is a Cauchy problem. Now you have understood what is a Riemann problem. So this is the Riemann problem. Let us solve this Riemann problem with respect to this conservation law, assuming that this is the correct conservation law. All right. So let us find out what is the solution. So you can see here that we know that solution, yesterday we looked at it. So what is the solution? X is equal to xi, if you remember, t times f of xi. f of xi was f of c of u. Is that right? But here it is c of u is nothing but u itself. So it is nothing but u naught xi. And what is u? U is equal to u naught xi. So in fact, this is your x is equal to, I could have written here u itself, x is equal to xi plus u. U is nothing but u of xi. Along these characteristics, u is equal to u naught xi. Is that right? Hello?
Yes, sir.
All right. So now if you look at the solution, we have to construct this, we have to construct a solution and you will see that how is it a weak, how this is a weak solution. So from here it is very clear that x is equal to xi plus t times u. So look at the characteristics which originate from this part of the profile. And now we are in the xt plane. This is your xt plane. This is your ux plane. So in the ux plane, this is your initial, right? Here u is equal to 0 and here u is equal to 1. Is that right? Here u is equal to 1. On this part, u is equal to 1. I should write here. So here in the xt plane, now I can write here u is equal to 0, right? This is your, sorry, x, and this is t. At t equal to 0, u is equal to 0 for x less than 0, and u is equal to 1 for x greater than 0. Right? And what is xi? Xi is a typical point here. Xi is any typical point. Xi could be 0, xi could be greater than 0, xi could be less than 0, any typical point on the real line. So now you can see here, when xi is less than 0, what are the characteristics? The characteristics, because on the left, u is equal to 0. So x is equal to xi. The characteristics are all vertical. Am I right? X is equal to xi. From each point, there is a characteristic emanating from the initial line. Is that right? Xi is an atypical point. X is equal to xi because here u is equal to 0. Is that right? Hello?
Yes, sir.
And therefore, what these characteristics do, we know they are the carriers of the information from the initial data. So whatever the value of u is available here, it will be taken over into the region. So here in the whole of this region, u equal to 0. These characteristics, right? They carry this information into the region, and so we get the solution in this region as u is equal to 0. All right. What about u is equal to 1? Hello?
Taking any positive value of xi.
U is equal to 1. So what are the characteristics? Characteristics are x is equal to xi plus u. X is equal to, hello, xi plus u. Xi is any point. So from here, what is the characteristic? Xi is equal to 0 and x is equal to, u is equal to 1. So x is equal to t. X is equal to t. This is the characteristic, emanating, leading characteristic of this family. And all these characteristics, in fact, they take this information. So you say here u is equal to 1. So all these characteristics, they take value u is equal to 1 into the region. But in this gap, this initial data is unable to control the solution in this gap. Hello?
Yes, sir.
So you see there are two possibilities. I can introduce a discontinuity. This is one solution. I introduce a discontinuity because I know a discontinuity has to satisfy this condition, that's all. So what are these? You take these because it is very clear. The characteristics are straight lines, right? Dx dt is equal to u. These are the characteristics. And u remains constant. So dx dt, is that right? Dx dt. So these are the straight lines. Characteristics are straight lines. So you can see here that these are the, straight lines emanating from here. So, but this condition must be satisfied. What it says, let us see. What this says, this says that dx dt, a discontinuity can be satisfied, can be introduced into the solution, which satisfies this condition. What is the flux function here? This is the flux function, u square by 2. Am I right? Hello? So jump in this means UL square minus UR square upon 2. Jump in F, jump in F. Is it all right? Divided by jump in U. Jump in U means UL minus UR. So this turns out to be half of UL plus UR. Is that right? I mean, this expression is guided by this Huguenot jump condition. It has to be satisfied if there is a discontinuity. I can introduce a discontinuity because, nothing stops me. Here, nothing stops me. This data is unable to control the solution in this region. So definitely I can introduce a discontinuity because this is a mathematical fact which has turned out that the solution on the discontinuity has to satisfy this. So if I introduce a discontinuity, let us see what is UL. I introduce a discontinuity into this region such that on the left of this, UL is 0 because here left side is 0. So it means all these characteristics, they extend, they emanate from this line. So half of UL is 0. I take UL as 0 and right is 1. So I extend this solution up to the discontinuity. So draw all these characteristics which are parallel to this, they have the same slope. So all this region up to here, it is U is equal to 0. Here U is equal to 1 and this is your half. So I can integrate it. This gives me x is equal to t by 2 plus some constant. This constant must satisfy because it originates from the point 0, 0. So when x is equal to 0, t equal to 0, this implies that constant is 0 and hence x is equal to t by 2 is the discontinuity which has to be introduced into the region. Yeah, according to this Huguenot jump condition, x is equal to t by 2 is the discontinuity. And on the left of this, the solution is 0. On the right of this, solution is 1. So I can write the solution now, uxt. This is one solution. On the left of, yes, this is 0. Then x is less than t by 2. And it is 1 when x is greater than t by 2. This is the solution. This is one solution of this. Now, do you think that it is a weak solution? Hello? Yes, because it's a discontinuity. Is that right? The solution involves a discontinuity, so it is a weak solution. Is that right? Hello?
Yes, sir.
All right. So this is one solution. All right. If I take another conservation law, you see, this is the solution with respect to this conservation law. Is that right?
Sir, yes, sir. Sir, I just one observation.
Yeah, sure.
In the initial problem, from where you have started the CU, or you taken U to be smooth C1 function, and you just land up that even though we have a smooth function or a very nice differentiable function, we can have this phenomena of the weak solution, right? But in this case, when we actually see this U is prescribed in such a way that it must have some discontinuity on some on some line, and we are actually just looking out for that particular slide, you can say, where it has, then this weak solution is like, for the earlier one, weak solution समझ आता है क्योंकि हम differentiable solution expect कर रहे थे, अचानक से differentiability conditions track down हो जाती है, तो एक टाइम के बाद we have left with this weak solution concept. But यहाँ पर तो weak solution ही ढूंढ रहे हैं, मतलब यहाँ तो non differentiable solution ही ढूंढ रहे हैं.
हाँ, नहीं, कारण ये है ना, हमने कल यहाँ से ये बताया था कि ये जो इनिशियल वैल्यू प्रॉब्लम है, इसकी ये कंटिन्यूटी ऑफ द सॉल्यूशन ब्रेक्स डाउन.
यस यस यस,
यहाँ एक डिसकंटिन्यूटी आ जाती है सॉल्यूशन में.
हाँ हाँ,
ठीक है.
हाँ हाँ,
हम यहाँ से ही लेके चले थे, हमारी प्रॉब्लम ये थी हम कैसे इसको एक्सटेंड करें सॉल्यूशन को बियॉन्ड दिस ब्रेकिंग टाइम.
ओके ओके ओके,
तो हमने कहा एक डिसकंटिन्यूटी आ गई यहाँ पर.
हाँ 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 हाँ,
वो डिस्कंटिन्यूटी कहाँ से आई? वो यहीं से आई, यहाँ से, जो इस इनिशियल वैल्यू प्रॉब्लम में वो डिस्कंटिन्यूटी दे दी.
right sir, right.
So now the problem is how to resolve, how to extend this solution beyond this breaking time. Is that right?
Yeah, I get the idea.
तो हमको फिर शुरू से अब ये करना पड़ेगा कि उसके बाद में फिर हम लेंगे कि भाई डिस्कंटिन्यूटी आ गई सॉल्यूशन में, ठीक है?
राइट.
तो डिस्कंटिन्यूटी आ गई तो फिर ये एनालिसिस है इसमें. अब बताइए, आपको कोई डाउट है इसमें?
नहीं सर, बिल्कुल डाउट नहीं है. एक्चुअली सेम चीज में सिस्टम ऑफ डिफरेंशियल इक्वेशन में एक्सटेंड करना, मतलब करने की कोशिश कर रही थी, कुछ ऐसा ही. जैसे this is only one single PDE, but if we have ODs and we have some discontinuity in space variables, then how pictures come? But many things clear from this particular explanation of yours.
नहीं, वो ये डिफरेंट प्रॉब्लम है. हाँ, बट यहाँ पर ये हुआ कि हमारा सॉल्यूशन आफ्टर ए फाइनाइट टाइम ब्रेक कर गया.
राइट.
अब हम चाहते हैं कि यहाँ से आगे गाड़ी कैसे बढ़े. हमारी गाड़ी तो ये रुक गई.
राइट.
यहाँ तक हमारा सॉल्यूशन था.
राइट.
यहाँ हमारा स्मूथ सॉल्यूशन था, लेकिन इसके बाद से हमारी गाड़ी रुक गई.
And we are looking for the U for whole of x comma t जो है belongs to R cross R.
Yes.
Okay.
हाँ, ये हम पूरा xt प्लेन लेके चल रहे हैं.
xt plane.
xt प्लेन लेके चल रहे हैं. इसमें t पॉजिटिव है. t stands for times. Time is always positive.
Yeah, positive.
तो upper half plane.
Yes.
Is that right?
R plus cross R, you can say. Yeah.
तो ये ठीक है ना? आगे चलें फिर.
हाँ, बिल्कुल सर, बिल्कुल.
Yes, sir. We have to move.
All right.
Thank you, sir.
All right. Okay. So यहाँ हम आ गए इस जगह. हमने कहा कि देखिए, ये जो सॉल्यूशन निकाला है हमने विद रेस्पेक्ट टू दिस फ्लक्स फंक्शन निकाला है. अब यदि हम इसी डिस्कंटिन्यूटी का विद रेस्पेक्ट टू दिस फ्लक्स फंक्शन निकालें तो डिफरेंट आएगा. देखिए, ऑब्वियसली डिफरेंट आना है. क्यों? कि ये जो डिस्कंटिन्यूटी है वो बदल जाएगी. Am I right? हेलो?
Yes sir, फ्लक्स फंक्शन और जंप फंक्शन बदल
जाएंगे. तो ये डिस्कंटिन्यूटी, ये डिफरेंट सॉल्यूशन हो जाएगा. That is, let me write this as jump in the flux function, that is 1/3 of UL cube minus UR cube divided by the flux function, that is 1/2 UL square minus UR square. Is that right? This is a jump now. तो ये हमारा RH condition हो गई. Is that right?
Yes sir.
Yes, sir.
And now from here we get 2/3. So obviously यहाँ पहले slope 1/2 था, अब यहाँ slope 2/3. हाँ, so obviously एक खत्म हो जाएगा. UL square plus UR square plus UL UR, एक फैक्टर चला गया और यहाँ रह गया UL plus UR. UL minus UR cancel हो गया. Now again I will do the same thing on the left of this, because this discontinuity has to be fitted into this solution, into this region where we do not know what is the initial condition. These initial conditions, is that right? ये initial condition केवल इस region में है. ये वाला, this is not governed by this initial condition, this gap. So in this gap I can introduce a discontinuity, because this is a mathematical fact that the solution, in fact, it should be of this type. There should be a discontinuity. We can introduce a discontinuity. If we introduce a discontinuity, say, so again in that case, this is 2/3. So the speed is, yes, speed is increased. So the slope will be decreased. So this, instead of 2/2, it is 2/3t. Some discontinuity somewhere here. Are you following? Hello?
Yes sir.
It will be somewhere here, and the solution would be different. That is, uxt will be your 0 when x is less than 2t/3. Is that right? Because if this is your UL is 0, UL is 0, UL is 1, so it is 2/3. Is that right? And x is equal to 2t/3, the constant, because it emanates from this point 0, 0. So this is the discontinuity. And therefore the solution is this. Solution is this. On the left of this, the solution is 1 on the right of this. So look here, we get uniqueness of the solution. Anyway, this is, we get two different solutions using two different conservation laws. So because of the non-uniqueness of the conservation law, is that right? The weak solution ceases to be unique. This is one problem. Although we have extended the notion of weak solution, but then there is a problem. The problem is this, because of the non-uniqueness. So, all right, non-uniqueness of the conservation law can be taken, can be resolved by, recourse to the, physicists can tell you that, oh, no, this is not the correct conservation law, this is the correct conservation law. So, it is an experimental fact, you see. We have to depend on experimentalists. They will say that which one is correct.
Yes, sir.
So if this is the conservation law, it is fine, all right. But even if you select one conservation law, even then there are initial value problems where the solution is not unique. So let's take another initial value problem. Say ut plus ux equal to 0, and this is the differential equation, and this is the initial condition ux at t equal to 0 is equal to u naught x, and I take this as 0 when x is 0, and I take this as 1. Am I right? Hello? Just opposite to what I have done here. Here it was like this. Sorry. On the left, I think, yeah, it is here only. So on the left it was 0, on the right it is 1. I will take on just the other way around. So this is 1, opposite of that. It is, am I right? Yeah. So I will take just opposite of this. So this is u is equal to 1 and 0 when x is greater than 0. Let us see what happens. In this case, what happens? This is the ux plane. On the left, u is equal to 1. This is your initial profile. This is your ux initial profile. On the left, u is equal to 1 in the ux, right? And here u is equal to 0. Here u equal to 0. Let us see what goes on in the xt plane. In the xt plane, because we have to look at the characteristics. These characteristics, they span the solution surface, so we have to focus only on the characteristic curves, right? They span the solution surface. So here, look here on the left, u is equal to 1, on the right, u equal to 0. So it's very clear that the characteristics emanating from this part of the, what are the characteristics? X is equal to xi plus t times u. Am I right? Hello? U is nothing but u naught. What is u naught? This is your initial profile. U naught on the left it is 1, on the right it is 0. So on the left it is 1, so x is equal to xi plus t. So the leading characteristic emanating from this will be x is equal to t. Am I right? Hello? All these characteristics, they emanate from this part of the real line, and they will take this information into the reason. Now from u is equal to 0, what are the characteristics? Hello? Tell me, what are the characteristics showing from this part of the line? When u not equal to 0, simply x is equal to xi. So these are the characteristics emanating from this part of the real line. Can you see? This is the reason, which is multi-value. Okay? Hello? Because characteristics, last time we noticed that the problem arises when the characteristics intersect. When the characteristic intersects in the xt plane, in the ux plane, the solution develops a vertical slope. Is that right?
Yes, sir. Yes, sir.
So a discontinuity has to be fitted, no doubt. It has to be fitted into this reason. This discontinuity. Look here. I think I just mentioned one more thing. This is one solution. The other solution could be, you can see here. You can see if I take all the characteristics emanating from, these are the straight lines. All these lines, they take values from 0 to 1. So you can see here that u is equal to x by t is the solution. U is equal to x by t is the solution when x lies between 0 and 1. I'm sorry. X lies between 0 and 1 in this reason. You can see. Because it satisfies the differential equation identically. You say ut, put ut, what is ut? Minus x upon t square. Is that right? Hello?
Yes, sir.
And what is the second term? U is your x by t. And what is ux? 1 by t?
1 by t.
Identically satisfied. Is that right?
Yes, sir.
So this is a solution. So this is another solution, you see. U is equal to your, I can write this as U is equal to, this is x by, in this reason, that is U is equal to 0 when x is less than 0. This is the boundary of this reason, less than 0. This is x by t, and x lies between 0 and t. Is that right? Hello? And it is 1 when x is greater than 1. This is another solution. So you see, there is a problem. This problem is because of introducing, right? Because extending the notion of solution, it extends discontinuities as well. And if this is the case, then of course this condition has to be satisfied to the weak solution. And if this condition has to be satisfied, this is one solution. Let us forget this, not conservation law. I'm talking about this conservation law only. If I take this conservation law into account, you look here, this is, one solution, and this is another solution. Are you following?
Yes.
So the non-uniqueness because of the conservation law. Is that right? And non-uniqueness of the, now you can see here, so this is another case. So here definitely, because the characteristics intersect, I have to introduce a discontinuity into the reason. Can you tell me again what is the discontinuity? The flux function on the left, assuming I am not, because if I take different conservation laws, I will get different solutions. I just mentioned one, conservation law. What is that? ud plus u square by 2x. This is equal to 0. So if I fix this conservation law, then in this case, yes, this is the solution which we have determined. That is here on the left, ul, only that is changed. That 1 plus 0 divided by 2, is that right? ul plus ur divided by 2, and x is equal to t by 2. So this is the solution, and the situation is somewhat like this. Here the characteristics, they don't emanate, but they impinge on the characteristic curve. This is the situation, this solution, this is your u is equal to 1, and this is your u equal to 0. That is, the initial information is absorbed by the discontinuity in this case, right? Obviously, you can see that your solution is, it involves a discontinuity, so it is a weak solution. This is a weak solution, right? This we have already determined. So, so now you have seen that there are two different cases. Then in this case, the characteristics intersect, and in this case, characteristics, they don't intersect. There remains a gap, and there, of course, this initial data is unable to control this solution. So we are free to introduce a discontinuity. So you can see that, problem is how to resolve this problem. How to resolve this problem? I tell you that not only that, there are infinite number of conservation laws. For example, if I take this problem, look here, u is equal to 0. Absolutely, there is no disturbance initially. There is no disturbance. Initially. All right. Then I introduce a discontinuity here. Look here, because discontinuities are to be introduced into the solution, right? Which satisfy RH condition. That is the requirement. Satisfy RH condition. So obviously the characteristics, they will emanate from here. These are the vertical lines. This is the fact of the thing, because when u is equal to 0, x is equal to xi. The characteristics are vertical. Here also x is equal to 0, so the characteristics are vertical. They will take this information into the reason. So here u is equal to 0, here u is equal to 0, and I take this as, so if I take this u to be, say, here, suppose there is a discontinuity, I can introduce a discontinuity. How? I take u is equal to 1, and here I take u is equal to -1. You see, mathematically it is correct. This is what I am saying. Please try to understand this point. This is the initial condition. Initial condition says that in this region you will be 0, in this condition you will be 0, but here I am free. I can always introduce a discontinuity. This is your x is equal to what? This is your x is equal to t by 2. This is your x is equal to minus t by 2. That is minus 1 plus 0 divided by 2. So discontinuity is admissible. Here x is equal to 1, minus 1 satisfies the RH condition, satisfies the RH condition, satisfies the RH condition. Do you think? Hello? Hello, are you following?
Yes, sir. Yes, sir. That
You
means
see?
we are free to do, I mean, in the region where we are not specified any initial condition, we can give it.
The initial condition is satisfied.
No. After initial conditions on characteristics, the leftover part.
Now, see, I am given only the initial condition, which is satisfied, which is satisfied.
Yes.
Now, rest. What I say, I can always introduce a discontinuity.
Right.
So, and mathematically, it is 100% correct. There is nothing wrong with it. Why? Because this discontinuity which I have introduced satisfies the RH condition. Dx dt is equal to jump in f divided by jump in u. I have assumed, I have taken the unique, conservation law, ud plus u square upon 2x equal to 0. A unique, I say that all right, this is the unique conservation law, right? This is the unique conservation law. Some physicists have told me that though you have to take this conservation law. So all right, I will take this conservation law, but even then, if the conservation law is uniquely specified, there is a problem. What do you expect if if there is no disturbance? Will there be, what kind of solution would be there? Tell me. There won't be any solution. I mean, if the initial disturbance is 0, how a non-zero disturbance can be created out of a zero disturbance? Hello?
Yes, sir.
This is, I mean, something, a very strange example, but mathematically it is correct.
Yes, I know. Physically, it seems.
Physically, it seems very
but
different, but mathematically, it sounds.
Physically, it is not acceptable.
Yes, sir.
This physically,
Physical model, so that it can be
yes,
verified.
physically
The
not
world is not
acceptable.
possible. Yes, sir.
Not acceptable, but mathematically 100% correct. Because you see, in this reason, these are the reason A, B, C, D. This is a constant state. 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 It satisfies. Each constant state satisfies this. Is that right? Hello? Because U is constant. This is 0, identically satisfied. How? I have introduced these discontinuities. 100% justified because they satisfy the RH condition. Is that right? It is half of UL plus UR. This is your half of, is that right? UL square minus UR square upon 2 divided by UL minus UR, you get only UL plus UR. So here it is 0, here it is 1. So this is mathematically correct. It satisfies this. It satisfies this. This satisfies. So 100% mathematically correct, but physically not acceptable. What do you think? Hello?
Right,
We have to
sir,
present
right.
the model.
So this problem was resolved by the great mathematician Peter Delax. Peter Delax is still alive because this is not very old. It is of a very, I told you yesterday, problem, I mean, recent origin. People, they started working on it only in late 50s and early 60s. But this man is still alive. He contributed a lot towards this subject, and he has written a book also. Yesterday I mentioned about this book by Peter Delax, Hyperbolic Partial Differential Equation, something like that. That is the title. What did he say? Because we don't have any stability criterion. So we need a mathematical criterion which introduces uniqueness into the solution. And very beautifully he said that a discontinuity has to be introduced into the solution. First statement. And I tell you, very rigorously these statements have been proved. Very, very rigorously. First, a discontinuity has to be introduced only when the characteristics intersect. That's we found that this problem, in fact, when the characteristics intersect, You see, this problem started only when the characteristics intersect. Then you get a problem. Is that right?
Yes, sir. Very first point where the
Yeah, that's right. So first he said that a discontinuity has to be introduced only when the characteristics intersect. And secondly, he said the characteristic speed, that is f dash at ul, is greater than dx dt, is greater than f dash ur. Oh, wonderful result. You see, it is very rigorously proved. What it says, the characteristic speed on the left,
it
f
is
dash ul.
basically.
What is f dash ul? Yeah, I think I will remain. I will. You see, this is the I've written somewhere. Yeah, this is ut plus ufx. Yeah, just 1 minute. Yeah, here. What is dx dt now? C dash u. This is nothing but f dash u. Is that right? Hello? So
Yes.
this is the characteristic speed. So what he says, that the characteristic speed on the left, characteristic speed on the left of the discontinuity. What is this? U is equal to 1. This is the characteristic speed on the left. Characteristic speed on the left of the discontinuity. This is the characteristic speed on the right of the discontinuity. The speed of the discontinuity has to be intermediate between these two values. Is that right? Hello? This is called Lex's criterion for uniqueness. And this is, I mean, really a wonderful contribution by this person. He is the, I mean, recipient of Euler prize.
In 2005, yes, sir.
So what he says, so look here, if we look at this criterion, this is not valid, because the characteristic speed on the left should be greater than the characteristic speed on the right. It is 1 and here it is 0, so it does not satisfy this condition. Are you following?
Yes, sir. Yes, sir.
This does not satisfy this condition. Characteristic speed on the left is less than the characteristic speed on the right, violates this condition. So this is not possible. Here also, the characteristic speed on the left is 0. The characteristic speed on the right is -1. But anyway, these two are wrong, and therefore this is not a physically acceptable solution. So what he emphasized, that solutions which violate this are not physically acceptable.
Okay.
Is that right?
This is a strong
now,
result. That
if you-
technically
Very powerful results.
a very powerful result in that.
Very powerful, right. Now, if we look at various results which we have just discussed, let me see, these papers, they get mixed. Yeah, right. So look here, if I take this one, u is equal to 0, u is equal to 1, I cannot introduce a discontinuity here. Are you following? Here, you see, there was a freedom when this result was not available.
Yes, sir. But
When
now,
this result was not available, I had a freedom. So if I had a freedom, I introduced a discontinuity. Mathematically, it is correct because it satisfies the RH condition.
Right.
So here again, I cannot introduce a discontinuity, and this is the unique solution. Then u is equal to x by t in this region, right?
Right. That means because it violates the Lex criteria.
Right. Exactly.
Yeah.
So this is the criterion propounded by this great mathematician, says that a discontinuity has to be introduced into the solution only if the characteristics intersect. If the
if this discontinuity was introduced before the lax, it will gives you the unique solution of the.
Pardon? What is
The uniqueness will be achieved after the lax criteria.
not assumed? It turns out to be a unique solution.
Yeah.
Oh, acha, again, I will have to do it now. You look here. I will have to do it. I take this example, ut plus ux equal to 0, right? And the assuming, say, u is equal to u naught x, all right? And this is your 1 when x is less than 0, and this is 0 when x is greater than 0. Is it all right? This is one problem, right? I discussed this one problem. So let us see what should be the solution according to Lex. According to Lex, what is the solution? The solution is this. look here, in the xt plane, on the left, it is u is equal to 1. In the x, I'm talking about the xt plane. The solution I know that x is equal to xi plus t times u naught of xi. And what is u? U is equal to u naught of xi. This is the analytical form of the solution. Here u is equal to 0. This is the scenario now. Is that right? Hello?
Yes, sir. Yes, sir.
So the characteristics from this part, will be this. These are the characteristics. They will take this information, u is equal to 1 into the region, and these are the characteristics. They will take this into the region. Is that right? Characteristics, they intersect, and therefore a discontinuity has to be introduced according to Lex's criterion. Right?
Right.
Lex's criterion. So a discontinuity should satisfy RH condition. Not discontinuity is not arbitrary. Not arbitrary we can fix. It has to satisfy the RH condition. What is RH condition? dx dt. Right? The discontinuity x is equal to x of t. This is equal to jump in f divided by jump in u. Assuming that the evolution takes place according to this conservation law, ut plus u square upon 2x equal to 0. Right? Assuming physicists told me that this is the correct conservation law. And if it's the correct conservation law, then the solution must satisfy.
Lex criteria.
No, this both. It has to satisfy both. So you see, it satisfies because the cutter speed on the left is 1 and the cutter speed on the right is 0 automatically. It has I have to introduce a discontinuity into the region. So you get a unique solution. Now it is a unique solution. Here you simply get 2. On the left it is 1, on the right it is 0. UL plus 0 upon 2, x is equal to t by 2. X is equal to t by 2. X is equal to t by 2. This is the solution, and these are the characteristics which impinge on the discontinuity emanating from the initial data. That is, the disturbance is absorbed by the shock. You see, such a discontinuity is referred to as shock then. It is called a shock or a shock wave, because the solutions, in fact, it is a weak solution. What is shock wave? It is a weak solution. Right? When we say wave, it is something related with physics, has nothing to do with mathematics. But shock wave is nothing but the solution, weak solution of a conservation law.
Yes, sir. Yes, sir.
For a mathematician, shock wave is a weak solution of a conservation law. For a physicist, yes, these are the discontinuities across which the flow and field parameters undergo sudden and abrupt changes. But it is not an imagination, you see. These discontinuities, they arise. They arise. You see, the jet aircrafts moving with supersonic speed, they have seen with naked eyes these waves emanating from the nose and also from the wings. Naked eyes. And across these shock waves, you see, all these physical variables, say density, pressure, temperature, entropy, they undergo sudden and abrupt changes. As a result, some undesirable vibrations propagate along these waves, and which in fact influence the balance, stability, and control of the jet aircraft. So researchers have been carried out how to minimize these effects which propagate along these waves. So accordingly, they change the shape of the nose, that how it should look like, aerofoil and wings. So a lot of work is still going on, you see, but now still we don't have supersonic jet aircrafts. Right? Researches are being carried out. It is in progress that how to take care of these shock waves which emanate from the nose and from the wings, how to reduce their strength. So anyway, so is it clear? Now the solution is called a shock. So it's a weak solution. A weak solution which satisfies RH condition and Lex's criterion is called a shock wave. or a shock solution anyway. What is shock? Shock, in fact, is a weak solution. It is a weak solution of an initial value problem involving a conservation law. Is it all right? Hello?
Yes, sir.
So the other problem was, look here, it was if I take this initial condition to be like just opposite of this, 0, when x is less than 0, if x is greater than 1, what is the scenario here?
Then they are not intersecting.
They are not intersecting, so I will not I will
I
not
cannot introduce the discontinuity in between.
otherwise there will be a problem because it will violate the Lex's criterion, and therefore the solution, in fact, what happens, these are the straight lines, these are the characteristics emanating from 0, 0, which take all the values between 0 and 1, and the solution is u is equal to x by t. How does it follow? It follows from here, because xi,
Yes.
u is equal to x by t, it follows from
This is the only solution of this.
Yes, this is the only solution of this initial value problem.
Yeah.
Right? That is uxt, this is equal to your 0 when x is less than 0.
Under the consideration of Lax principle, right?
Yes. And this is your 0, 0 less than x less than t. And this is your 1 when x is greater than t. This is the unique solution. Unique solution of this initial value problem, which, of course, the conservation law is this. Is that right? Assuming that the conservation law is uniquely specified.
Yes, sir. Very right.
So, I mean, this is, I think, is it clear that whatever I have discussed up till now?
Yes, sir. So, other than,
Yes, any query, please do ask.
you started with some particular kind of example, this ut plus ux is equals to, is there any other kind of differential equation?
This is first order. You see, I'm just because this is very important. That's why.
Yeah, definitely.
And at the same time,
on undergraduate level too also, and
the Riemann problem. The Riemann problem. It's a building block for higher order equations. Right? More complicated equations. So this solution of the Riemann problem is a very, very important problem in the literature. Right? I mean, that's why I considered Riemann. Let us consider one more example. Okay.
Yes, sir.
Example. Let us take this equation only. This is Inviscid-Burgers equation, right? This is Inviscid-Burgers equation, and consider this, assuming that the evolution is governed by the conservation law. This is very important because conservation law is not fixed. This has to be specified by the conservation law. Ut plus u square upon 2t, this is equal to 0. Consider this, assuming that this is the conservation law, and together with initial data, let me take this situation when here it is u is equal to 1, here it is 1 minus x by a, and this point is a, and here u is equal to 0. This is the initial profile, u versus x. Is it all right? Hello?
Yes, sir.
The profile is a continuous one now.
Yes.
The initial profile is continuous, and we will see that how it breaks down. We will see. So look here. So this is, let me write u naught x. U naught x is 1 when x is less than 0. It is 1 minus x by a when it lies between 0 and a. And it is 0 when x is greater than a. Is that right? Hello? This is the initial data.
Yes, sir.
All right. So now you have to tell me that how to start and what to do. So what should be the first step? what should be the first step? You write the analytical form of the solution.
Yes,
What,
sir.
what is
First, we can
the,
have the characteristics of this.
what do you say?
We can draw the characteristics.
Yes. So first we will write the analytical form, then we draw the characteristics.
Yes, yes.
Analytical form is this: x is equal to xi. We have already seen u naught xi, and u is equal to u naught of xi. U means is a function of x and t. U as a function of x and t is nothing but u naught of xi. Is that right? This is the analytical form of the solution which we discussed yesterday. This is the analytical form. Is that right? Hello?
Yes, sir. Yes, sir.
Okay. So now you look at it that what are the characteristics? What are the characteristics emanating from this part of the line less than 0? Yes, these are the characteristics. Am I right? Because xi here, xi is in a typical point. This is the leading characteristic, 0, right? At 0, xi is equal to 0, it is t, and u naught is 1. So x is equal to t is this point.
Yes.
Sorry, this line. And rest characteristics are, these are the characteristics, and they will take this information into the reason, namely u is equal to 1.
Right.
Is it all right? Huh?
Right, sir. Right.
All right. What are the characteristics showing? So I will write that anyway. I will write finally that this is the solution. What are the characteristics showing from this part of the line A2? Yes. Let me say that this is point A.
Then u is 0 there in that case, and
These are the vertical characteristics.
this is x is equals to.
U equal to 0. Here u is equal to 0. Is it all right? Hello?
Yes, sir. Yes, sir. Right.
And in this reason, what happens? The solution u naught xi is given by
1 minus
xi
xi.
by a. Very
Yes.
good.
1
1
minus.
minus xi by a. Very good. So you plug this here. So what are the, let us see, what are the characteristics? X is equal to xi plus t times 1 minus xi by a. Is that right? Hello?
Yes, sir. Yes, sir.
Yes, but you can see here that this point. What are the coordinates of this point here, where these two characteristics intersect?
1, 1.
A. This point is x is equal to a. This is x is equal to t. So it is a. Is that right? X is equal to a. T is equal to a. Am I right? Hello?
Right, sir. We can use this information and then.
Yeah, and beyond this, in fact, there is a multi-valued reason.
Yeah,
All
sir.
these characteristics,
Characteristics are intersecting. Yes.
yeah, they are intersecting. So up to here, the solution is smooth. You can see here that this is the separation line AA. Up to here, you get a perfectly continuous solution. For t, this is your xt plane. For t, this is your t. This is t. This line is t is equal to, hello? This line is t is equal to a. Am I right?
Yes, sir.
So in this interval, in this strip, from 0 to a, in this open interval, we have a perfectly, regular continuous solution. Look here.
Right, sir. Right.
Let us see that what are the characteristics. X is equal to xi, is that right?
Yes, sir.
So you can see here, take any point and it is going to intersect at AA, and x is equal to a, t is equal to a. When x is equal to a, t is equal to a, they satisfy this equation. So all these characteristics emanating from here, they will, yes, it will be like this. These are the characteristics which emanate from here, but here the solution becomes multi-valued at AA, because different characteristics, they carry different values of u. Am I right? Hello?
Yes, sir.
And at this point, the solution becomes multi-valued. So at AA, the solution breaks down. Now, how to get the solution in this region? Our objective is to find the solution in this region. So the idea is saying this is implicit. So what we do, we express xi as a function of x and t, and we plug it here. Hello?
Right, sir, right.
So u naught xi is this. I will solve it for xi and plug here. So what do we get? So x minus t, right? Transposing this to the xi, that is 1 minus t by a. Please look at this calculation. I should not commit any mistake. Is that right? So what do we get? Xi by a into a minus t, and therefore xi by a is equal to x minus t upon a minus t. Xi by a is known to me, and therefore, yes, I can write these characteristics, as x is equal to t, and you can see what is the solution. Let me first write the solution. The solution in this region will be u naught xi. This u is equal to u naught xi is the solution. And what is u naught xi? 1 minus xi by a, that is x minus t upon a minus t.
3.
You get a minus t minus x plus t upon a minus t, and you get a minus x upon a minus t. So the solution in this region is this uxt. Uxt is nothing but u naught xi, and u naught xi, and in fact this is the solution. U is equal to u naught xi. U naught xi is a function of x and t. This is your a minus x upon a minus t. Is it clear? Hello?
Yes, sir, yes, sir.
So I can write the solution. The solution for t greater than or equal to 0, less than a, in this open interval. What is the solution? On the left one, when x is less than 0, in this region, the solution is this, that is a minus x upon a minus t. In this region, that is x varies from 0. I'm sorry, this is x is equal to t. X is equal to t. X is less than, this line is x is equal to t. So this is x is greater than t. X is greater than t and less than a. Am I right? Hello? Please check. And in this region, the solution is 0 when t is greater than a. Is that right? This is the solution in this interval.
Yes, sir, yes, sir. Yes.
And it is a weak solution, although you say there is no discontinuity at all. Do you know why it is a weak solution? Hello?
Hello, sir, hello.
Is it a weak solution?
Sir, within an interval from 0 to a of that t, it's not weak solution, but if we go after it.
No, it's a weak solution.
It is still weak solution.
Why it is a weak solution? You can see about x is equal to a, this line. On the right, u is equal to 0.
Okay.
On the right, u is equal to 0, but on the left, u is equal to on the left of this line, x less than 8 is a minus x upon a minus t. Hello?
Yes.
Now, if you differentiate, then
With respect to, okay, yes.
no, you see, this is the boundary where the discontinuity appears. You see, here u is equal to 1. If you differentiate, here u is equal to 0, but here it is not. It is non-zero on the right.
Yeah, I understand.
So the discontinuity is in the variables or in the derivatives. It is a weak solution.
Right.
By classical methods, you can't get the solution of this initial value problem, right? No classical method. You have to make use of this weak solution method, right?
Right, sir. Right.
So this is the solution. Now the bigger problem: how to extend this solution beyond this breaking time? We are interested in finding the solution for t greater than a. So a discontinuity has to be introduced here, according to.
Yes.
Hello?
Yes.
A discontinuity has to be introduced because it's a multi-valued reason, and our objective is to replace this multi-valued reason by a discontinuity which is not arbitrary. It must satisfy the RH condition. Is that right? It must satisfy the RH condition. Yes or no? The discontinuity emanating from this point, it goes into this region. This is the boundary of this region where the characteristics they intersect.
Yes, sir.
And therefore, can you tell me that what the solution would be? On the left, it is clear. It is 1 on the left because these are the characteristics. There is no intersection.
Right.
So on the left, it is 1. On the right of this discontinuity,
It is 0.
Here I have to find what is your RH condition, dx
dx by dt is equals to bracket f, jump in your
f divided by, so assuming that this is the criterion that ut plus u square by 2x equal to 0. Or is that right? This is the conservation law. Assuming that this is the conservation law, because if you change the conservation law, it will be a problem. The problem is this: conservation law is fixed, right? You have been told by physicists, look, this is the conservation law. So conservation law. So you see, mathematicians cannot solve such problems unless they know the conservation law, and conservation law will be decided by the physicists, by the engineers, isn't it?
yes.
By the experimentalists. So this is the correct conservation law. So once you get, for example, in water, your shallow water equations, you see, if you look at the governing equations of the shallow water, I mean, these are the physicists and engineers who have said that, look, this is the correct conservation law, and you have to follow only that conservation law. Are you following?
Yes, sir.
So here dx dt will be your jump in f divided by jump in u, and jump in f is half of ul square minus ur square divided by ul minus ur. This is half of ul plus ur. On the left of this discontinuity, u is 1. On the right,
It's 0.
so this is 1 by 2, x is equal to t by 2 plus some constant. How to determine this constant? How to determine this constant?
So we use that condition of xi, this
Which condition?
mid between condition of this.
Which condition?
That we have given
RH
the view
condition.
xi.
This RH condition we have used. Using RH condition, we have got this form of the discontinuity. X is equal to t by 2 plus constant. Now constant is to be determined.
That constant can be determined only with the help of this initial condition, which is given in the middle step.
What
Use xi is equals to 1 minus xi upon a when xi is between 0 and 1, or something.
No, you see,
Isn't it?
this is the point from where it emanates, and we know the coordinates of this point, AA. This discontinuity originates from this point whose coordinates are AA, x is equal to A, t is equal to A, yes or no?
Yes.
So we have to make use of this condition. We have to introduce a discontinuity emanating from this point AA. Up to AA, we have in this open interval, we have a perfectly continuous solution, right?
Yes, sir.
It is weak in the sense because there is a problem with the derivatives, but we have a continuous solution here. Is that right? Here the solution becomes multi-valued at x is equal to a, t is equal to a. So at x is equal to a, t is equal to a, constant is a by 2. Am I right? Hello?
Yes, sir.
And therefore the equation is t by 2 plus a by 2, or you can write a plus t by 2. X is equal to a plus t by 2. So the solution will be, you can write, I think there is no need of drawing this line, unnecessarily it will create a confusion. I will write this line, x is equal to a plus t by 2. This is your, x is equal to a plus t by 2. So up to here the solution is your this, and then there is a discontinuity. There is a discontinuity, its slope is this. X is equal to a plus t by 2. This point is AA. Here the solution is known. In this region, the solution is known. And in this region, now I can write the solution. Is that right? This is the discontinuity. This is the discontinuity. On the right, u is equal to 0. On the right, u is equal to 0. On the left, u is equal to 1. So the solution for t greater than 1 would be uxt is equal to what? Tell me. On the left, it is 1. So 1 when x is less than what? A. Am I right? When x is less, oh, I'm sorry, x is less than a plus t by 2. This is x is equal to a plus t by 2. Is that right? This don't confuse with this line. This is the line x is equal to a plus t by 2. Is that
Yes,
right?
sir. Yes, sir. Yes.
This is the reason, and this is your x is equal to a plus t by 2. Right? On here, u is equal to what? 1 on the left. Here, u is equal to what? 0. And here, u is equal to, we have determined it is a minus x upon a minus t. Is that right?
Yes, sir. Yes, sir.
So look here, for the solution for t greater than a, the solution is 1 when x is less than this, and the solution is 0 when x is greater than a plus t by 2. So this complete solution of this initial value problem consists of 2 time intervals. Is that right? One interval is this, in which this is the solution. It is a continuous solution. One interval is this, in which the solution is a discontinuous. It involves a discontinuity at this point. And it is quite apparent from here that as t approaches a, I mean, this solution is undefined. It's very clear because here it is a multi-valued reason. Different characteristics. Now you can see here, this is a constant state. It satisfies this differential equation identically, ut plus, where I have written it. I have written it somewhere. Yes, it is here. Ut plus ux. So u is equal to 1 satisfies it. Right? This entire one, u is equal to 1 satisfies it. U is equal to 1, 0 satisfies this identically. In this reason, it satisfies identically. You can see here, u is equal to a minus x upon a minus t. U is equal to a minus x upon a minus t. It has to satisfy this equation. What is ut? Ut will be your a minus x upon a minus t whole square with minus sign. Am I right? Hello? Plus u, that is a minus x upon a minus t into ux. And ux will be what? Derivative, that is minus 1 upon what? Am I right? Ux upon a minus t. Is that right? I am differentiating with respect to x. That is minus 1 upon a minus t.
Yes, sir.
So you see, this should give you identically 0 solution. And it is so. Am I right?
Yes.
So is there any problem? Ut plus ux. Is there any mistake in the calculation? Please check, is there any mistake in the calculation? Because this should turn out to be 0. I don't think it is 0. Am I right? A minus t whole square. This is minus of a minus x. No, there is plus minus mistake somewhere. So where is the mistake?
So there must be mistake in the solution part only, I think. You could see.
Can you identify this? Can you identify this mistake somewhere? Where is this mistake? Calculation mistake?
Second, sir. Second. X minus t. 1 minus
Oh, I think, yeah, there is a problem. A minus x upon b minus 2 of t less than x less than a. Yes. And this ut will be your. Oh my God, this is correct. I'm sorry. You say differentiating with respect to t minus sign, then again, oh, this is correct. This is plus because a minus t is here. Am I right? Hello?
So can you show the actually your the page is
Yes.
yes.
No, this is correct. There is no mistake at all. There is no mistake. We are differentiating with respect to t, it is a minus t, so plus sign will be there.
Yes.
And it is identically satisfied.
Yeah.
So this is the complete solution, whether it is clear to you. Hello?
Yes, sir. It's
And if you look at the profile, very interesting, you see, look at the profile, how this profile undergoes distortion. So at t equal to 0, this was the profile. At t equal to 0, the profile was like this. This from here to here, a, and this is your 1 minus x by a. This is all right. Here u is equal to 1. Here u is equal to 0. Now this is at t equal to 0. This is at t equal to. This is the profile at t equal to 0. This is your ux plane, right? This is your ux plane at t equal to 0. Now what happens when t is greater than 0? When t is greater than 0, and so look here how the profile has undergone change. When x is less than t, this is 0. So now it has moved. It is x is definitely greater than 0, less than t, and it is 1. So up to here, it goes up to here, okay? X less it is t, and then from t to a, x is greater than t but less than a. If you look at the slope of this, right? The earlier it was what? It was x by t, am I right? A 1 minus x by a, that is a minus x upon a. Is that right? Hello? The initial slope was a minus x upon a. But now it is a minus x upon a minus t. So it's slightly steepened. Slightly steepened. Is that right? Hello?
Yes, sir. Yes, sir.
And finally, when x is equal to a, yes, you get a shock, in fact. And this is the solution at x is equal to a. At x, what happens when t is greater than a? So this is the solution at t greater than a, that x is a plus t by 2. So here it is 0. It goes a little further. It is a plus t, right? A plus t by 2. At a plus t by 2, you get a discontinuity here. That is, the profile undergoes a distortion. Look here. What a continuous profile. Up to here it remains continuous, but at this here it is discontinuity. A discontinuity is introduced, so here it becomes a shock. Here it becomes a shock. A continuous profile, so what a wonderful result. A continuous profile terminates into a shock after a finite time, and we get the solution as we have written analytically. So please tell me whether is it clear. You see, let me ask the participants what they think. Hello?
Yes, sir. But I just want to know that after time t greater than a, then how it behaves? Just
Where at time t greater than
a.
Oh, definitely. You see, when you see this is between 0 and a, and it is for t greater than a.
Okay, then it's 0 only. Okay, I mean that's okay.
Is it all right? Hello?
Yes, sir. Yes, sir. Initially was this profile, and once the t is greater than 0 and less than a, it starts just the slope at that particular over a period of time. It's becoming more steeper and steeper in that way.
In this interval, see, so it propagates as a shock afterwards. That's all.
Yes.
After this time, t greater than a, the solution behaves like a shock only. A shock propagates.
Shock propagates, right, sir?
Is it clear to everyone?
Now we understand the meaning of shock also.
Lakshmi, you ask the participants, do they have any question? Lakshmi?
Yes, sir, please.
Please ask the participants, do they have any problem or do they want me to repeat something?
Okay, sir. Okay, sir.
So if they have understood, now they have to explain to me how to do this problem. 0, when x is less than 0, this is x by a. When 0 less than x less than a, and it is 1 when x greater than a. I mean, this is the initial profile. So geometric, I mean, what is the graph of this? Here it is u is equal to 0.
Right.
This is your ux plane. Here, between 0 and a, it is x by a. So it is.
This
so
is a straight line.
It is, yes, having the slope. Is that right?
Right, sir.
So,
Slope is by
And
a.
then it goes 1.
Right.
yes,
And then
beyond
with
this,
the horizontal.
yes, this is
equal
u
to
is
1.
equal to 1.
Right.
So please tell me if people, they have understood what will be the solution of this problem. It is a continuous profile.
Yes, yes, definitely. It is.
So again, somebody, please ask the participant, they should participate in this discussion. They should tell me, they should guide me now what to start, where to start. Hello?
Yes, sir. Yes, sir. Once
Please.
we know the solution, and first we do the characteristic. That's the usual method, the usual idea. X is
So
equal to
this is the analytical form of the solution we know.
u naught xi. And
And
u is
uxt is nothing but u naught of xi.
yes, right,
This
sir.
is the analytical form of the solution.
Right.
Now you can see here, go to the xt plane,
Then we
write
substitute.
down the characteristics. So u is equal to 0. From this point, yeah, what these characteristics are vertical lines. Am I right?
When you, yeah, it's a straight line. Vertical lines.
Vertical lines. So this is u is equal to 0. So you get in the whole region u is equal to 0.
Right.
Now here u is equal to what? X by a. Is that right?
Right.
Xi is an atypical point, so the characteristic is showing from this will take this information u is equal to xi by a. Am I right?
Right, sir. Right.
So our objective is to express xi as a
Xi
function
in terms of x.
of
Right.
x and t. So this equation would be x is equal to xi plus t times
Xi
xi
by
by a, and we get xi is taken outside. What we get? A plus t by a. Please check this calculation.
Correct, sir.
And we get xi is equal to ax or xi by a. I need xi by a. So xi by a is equal to x upon a plus t. So the solution would be xi. Look here, what are the characteristics? They will start from this 0. This is 0 and this is a. So they start spreading, you know, these characteristics, they start spreading.
right. Right, sir.
Is that right? And at x is equal to a, in fact, it is a upon a plus t. I mean, you can see here.
Then they are the straight lines. Yeah.
Right?
After a, yes.
So this is your when x is equal to when this point is a, the characteristic will be a plus t times x by a, and this x by a, isn't it? So they just intersect. Then what happens at this here? X is equal to, this is 1, so this is x is equal to t, and here all these characteristics are parallel to x is equal to t. This is the behavior. So you get a perfectly continuous solution. In fact, this is the boundary of this region where it spreads. This is expansion takes place here. Expansion. And here u is equal to, here u is equal to what? 1.
1.
So we have a perfectly continuous solution. I can write the solution. So there is no discontinuity at all. But even then it is a weak solution. You have to tell me why.
Because they are not continuous at the bound at these points. When it is passing from u to 0
At
to
A,
the expansion,
that's
then
the
they are
situation.
At the boundary,
Yeah, at the
of
boundary.
this region, there is a problem. Otherwise, it's a continuous.
Otherwise, it is flowing perfectly.
Yes. So uxt will be your, this is 0 when x is less than 0. This is your solution. What is the solution? We have determined u is equal to xi by a, that is x upon a plus t. X upon a plus t when x lies in this region, 0 to a, and then after that when x is greater than a, the solution is what? the value is u is 1. This is the solution, which is a weak solution, because you see, if you can see here, if you approach this point from right, the derivative is 0. But you approach this point from left, it is non-zero. So
Yeah.
derivatives are discontinuous across the boundary.
Right, sir. Right.
So that is the interesting thing. So it's a weak solution, and yes, for all it is valid. I mean, for all t, it is valid for all t now. You see.
So since because they are not they are not intersecting anywhere above, then
Characteristics, they don't intersect. If the
Yes.
characteristics intersect, we have to introduce a discontinuity.
discontinuity. Right. But
So
in
what-
this case, they are not intersecting, isn't it?
Yes.
Yes. Okay, sir. Yes.
So now only 5 minutes remain. I would have taken one more example, but I think it's all right because other participants, they are not taking any interest. So I don't feel very enthusiastic about the whole thing, and I'm really I do not know whether whatever I have explained it has been. I mean,
But till
Yes,
now,
it is
whatever
very
you have
clear, sir.
stated,
Till now, it is fine, sir.
I see.
It is very
you have
clear.
explained things very nicely, sir. Thank you so much.
Oh, okay.
Thank you.
So I think there is no. I can take one more example, but then it's all right. You pick up any book. I have told you enough references. This is Breshan, a very good book. Breshan's conservation laws, and then Breshan's book on conservation laws. There is another book by Smaller on shock waves and shock. This is it says reaction, diffusion equation, and shock waves. This is the title of this book. And then McCovin. This is on partial differential equations, and on conservation laws. Yes, of
Rendell?
course. Pardon?
Sir, Rendell, R.J. Rendell.
Yeah, very right. Rendell, correct. Leveq,
Yes, sir.
Leveq, Leveq, R.J. Leveq,
Yes, sir.
R.J. Leveq, and there are some other books. Yes, I have also written a book in that is CRC Press, 2010. This also deals with this similar stuff.
But sir, just I want to only one small question. Can I
Yeah.
just, आपने सर जो ये सारा कंसेप्ट हमने शुरू किया था बर्गर्स इक्वेशन visualizing these characteristics, so I think isn't it easy? Can I, if
Is there any question from the participant? Is there any question?
सर मैं एक सवाल कर रही थी, पता नहीं कुछ शोर मुझे लगा.
हाँ, बोलो।
मैं यही पूछी थी सर, आपने जो भी मोटिवेशन हम लोगों ने स्टार्ट की थी बर्गर्स इक्वेशन से, तो हम लोगों ने दिस विजुअलाइजेशन ऑफ कैरेक्टरिस्टिक्स एंड उनका प्रोफाइल, ये सब हमने देखकर ज्योमेट्रिकली फिजिकली अंडरस्टैंड करा. बट क्या अनदर काइंड ऑफ इक्वेशंस जहां पर कैरेक्टरिस्टिक्स आर नॉट इजीली वी कैन सी?
Why we cannot see? The theory is there. We can find the characteristics.
Yeah, we can find the characteristics, but every time is it so easy to just visualize the characteristics? They are not straight lines every time, isn't it?
Yeah, of course, they're not every time, but this is you have to look at it.
Okay.
You have to find that what are the characteristics.
Characteristics.
Not every time it will be straight line.
Okay, sir. Thank you, sir. Thank you so much.
These problems, simple problems, I have taken so that at least.
Yes, sir. Definitely. Simple problem से ही आप समझ पाओगे.
This is the motivation.
This is the motivation.
Some harder problems.
कि कई बार characteristics काफी quadratic भी आ जाते हैं कुछ इस तरह से, तो फिर वहाँ पर visualization.
When there is a non-homogeneous terms, then characteristic will not be straight.
Yes. Very right.
Okay. Thank you, sir.
Okay. So any other query? If there is no query, I think the time is going to be up.
Thank you, sir.
Okay, thank you very much. So, Lakshmi, can I?
Thank you very much, sir,
Yes.
for the very informative and interactive lecture.
Yes, yes. Thank you.
I am very sure that all the participants have gained the very deep insights
Yes,
about the concept of the differential equations.
yes, yes.
We are really grateful to you, sir, for providing your precious time for these sessions
Okay.
and putting the sincere efforts for all the participants.
Thank you.
Thank
Thanks.
you very much, sir.
Okay.
And I am really very thankful to all the participants who really make these sessions wonderful and effective in the sense to have interactive discussions
Yeah.
with
Very
Professor V.D. Sharma, sir.
okay. Thank you.
I am thankful to all the faculty members of Department of Mathematics, IIT, Professor Alka Tripathi ma'am, Head Department of Mathematics, for sharing their time for this event. Tomorrow again, we will connect with the same link at 3 p.m. for the upcoming sessions. Thanks to all.
All right.
Thank you. Thank you, sir.
Thank you. All right. So can I close this session now?
Yes,
Yes,
sir.
sir.
Okay. Thank you.